This lecture is going to go through a lot about polynomials, which is a type of function that you have definitely had a lot of experience with before. Now, this lecture is going to be very concept heavy. I'm going to be writing a lot on the board. We're not going to go through very many examples because there just isn't a lot to go through. A lot of this stuff is just visual, so I might draw a couple of pictures, but other than that, there's not really going to be too much work that comes out of here. It's mainly the ideas that come out of here that are going to get translated into bigger, tougher questions as we go through this unit. And those are the things I could ask questions on, okay? But this is probably one of the bigger units in the course. Typically, polynomials and these other functions called rational functions are lumped in together because they're so similar. You can do so many things if you do them one after the other, okay? So that's how we're going to do it. We're going to spend a couple of lectures doing polynomial stuff, a couple of lectures doing rational stuff, and then that's how we're going to go through both of those units. And the test at the end is going to involve everything up until the end of rationals. Okay, that's my goal at least. Okay. All right, so let's go over the definition first of a polynomial. Okay. Before we go through the actual definition, all I want to do is give you some examples of things that you've seen that are definitely polynomials. So, for example, you've seen linear equations, right? So let me just put a line here. And we'll go through some linear equations. Linear equations, so for example, anything in the form y equals mx plus b, so like 3x plus 1 or minus x plus 2. Those are all polynomials, okay? We also have quadratics. Okay? So things like x squared, but also, you can add terms to that. So x plus 2 squared, and it doesn't really matter how you write them. X to the 3 plus x squared plus 2x minus 1. All these things are also polynomials, right? Now, what a polynomial is, in case you've never heard of it before, is just a continuation of this. So you see how here we have a x term and a just constant term. Here we have a x squared term, a x term, and a constant term. We are just going to keep on adding terms after this. Okay, that's all the definition of a polynomial is. The only restriction is that the powers cannot be fractions; they have to be whole numbers. And you also have that you can't keep adding terms forever. You have to stop somewhere, right? So maybe now would be a good time to introduce the formal definition. And the formal definition is this: a polynomial function is a function in, okay, so with a variable raised to integer powers. Positive integer powers. So we're going to say natural powers. And coefficients. Okay. So there are two things that we need to dissect in this definition. Okay. Actually, let me present to you the alternative definition first. So the alternative definition is any function of the form, and this is where I don't really like doing this first because it's a little confusing with all the notation and terminology. But to put it literally, most books will present it like this. It's any function of this form. Okay, so that is probably more confusing than this. So let's go and dissect this first and see why it's the same thing as this. Okay, so a polynomial function is a function with a variable. In our case, our variable is x. So let me put that here. So our variable is x. Okay, raised to natural powers. So raised it to natural powers means that we have terms like x to the 1, x squared, x cubed, so on, things like that. Basically x to the n, where n is a natural number. Okay, I am sorry, I am writing like completely crooked. So x to the n, where n is a natural number. Okay? Now with coefficients just means that we can have a number multiplied in front of those terms. So like here we had a 3, and here we had a -1. We can put a coefficient in front of these. So now you can probably see why this is the exact same thing. The an minus 1, a1, a0 are just numbers, right? These are your coefficients. So the an minus 1, all the way up to a1 and a0 are just numbers. Real numbers. Okay? They can go in front of the x to the whatever, right? Meanwhile, you have these things, right? These are our variable raised to the power, right? So here we have x to the n. N is just some number, right? N could be, for example, 5 or 6 or 7. But the important part is that it's natural. It's a natural number, right? So again, something of the form of this. Right? Let's go over some examples of polynomials on the right side. So I'm going to erase this. So some examples. I'm not going to do any more linear or quadratic examples. I'm just going to do like examples that are not part of those categories because you've already seen enough of those. So we could do 3x cubed plus 2x squared minus 1. That's a polynomial. Okay. 5x to the 5 plus 4x to the 4 plus 3x to the 3 plus 2x minus 1. Or let's do plus 1. I tried doing a pattern and now I confused myself. Alright, okay, but these are like very easy to see examples. Some more difficult examples would be where these coefficients, the 5, the 4, the 3, the 2, the 1, and the 1, are actually just are just real numbers. They don't have to be integers like I've done here. So for example, I could do this. Pi x to the 6 plus 1/2 x to the 3 minus, I don't know, let's do 2 million x plus some other number. We'll do pi divided by 3. Okay? These can be any numbers you want. However, note that the exponents that x is raised to, so 6, 3, here there's an imaginary 1, and here there's a x to the 0. But we don't write that because x to the 0 is just 1. Okay? These numbers can be whatever the hell they want. But these numbers in the exponent, they have to be positive integers, natural numbers, right? 6, 2, 1, 0, they're all natural numbers. Okay? So maybe now is a good time to give some non-examples. So here are some examples of not polynomials. Okay? So the first thing that I could do is just have something that is not a power. So for example, I could just do root x plus 1 over x plus x to the 3. So you might look at this and think maybe it's a polynomial. After all, I can change these, right? I can make them x. This is the same thing as x to the 1/2 plus x to the -1 plus x cubed, right? Maybe this is a polynomial. No, it's not. It's not a polynomial. Try and think of why it's not a polynomial and look at the definition to really think about it. Okay? It's not a polynomial because of these. Okay? These are not natural numbers. The exponents have to be natural numbers like I did up here, right? 5, 4, 3, 2, 6, 2, 1, 0, 3, 2, 0, right? These are all integers, and here we have things that are not integers. It doesn't matter if this one's an integer. It doesn't. Okay? It's important that every single exponent is an integer. Okay? Here's another non-example. Okay? And that would be this. And this example and the next one I'm going to show you, those two together combine most of the misconceptions about polynomials. So once you've got these ones, you're pretty much good to go. Okay? So a not polynomial example is something like this. X to the 3 plus pi x to the 4 2 minus 1 over 3 x to the 1 over 3 plus 2. Okay? So the thing with this one is that it's almost a polynomial. This is fine, this is fine, this is not fine. This is not fine because the exponent is not a natural number, it's a fraction. Okay? So the two most common mistakes are not recognizing that these are natural numbers, and also being fooled by the rest of the function, which looks pretty polynomial, right? Like, the rest of it is fine. If this thing weren't here, it would be a polynomial, but because this thing is here with a 1/3 power, it is not a polynomial. Okay? Alright. I don't think I need to say too much more about that. That's just the definition of a polynomial, okay? Now, you may be wondering why it's useful to work with things like these. At the end of this unit, I'm going to give a lecture on something that's sort of unrelated to the curriculum, but is a really important application of polynomials and why we would want to study them. Okay? Because the things that we're going to be doing today and throughout this unit may seem pretty they might seem to be a stretch. Like, you might be confused as to why anyone would want to consider what these do, or why anyone's interested in what these polynomials are. But I assure you there's a very, very good reason. Okay? Alright. So now we're going to go to some concepts about polynomials. Alright. Let's see. Okay. So, some facts about polynomials. Okay, so the first fact is that their domain is always all of the real numbers. Now think to yourself why that should be true. And I'm going to tell you why. It's because, remember, by definition, any polynomial looks like this. an x to the n plus an minus 1 x to the n minus 1 dot 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 a1 x1 plus a0 x a0. Okay. And again, the an minus 1, a1, a0, those are just numbers, okay? The reason why they have different things in the subscript is just to differentiate between them, okay? This just means this is the coefficient in front of xn, this is the coefficient in front of xn minus 1, and so on, okay? So, the domain is all of the real numbers, because no matter what real number you put into here, it will always return a real value. There's never going to be any problems, right? You're just raising things to the power. The only way we know that it can have problems is if you have a negative square root, right? That's one way we could get a problem. And the other problem is 1 over 0 or 0 over 0 kind of issues. But you never get that with these. So that's already a good reason to study polynomials, is that their domain is everything. So they're defined everywhere. Okay? Here is another nice property about polynomials. Now you may be wondering why I'm not going to mention range. I'm going to not mention range because we're going to get to that, but later. Okay. So another fact about polynomials is that they're always continuous. Okay. Now I don't have the machinery or the and you don't have the technical knowledge to be able to prove this the way you should prove it. However, it should be pretty clear to you that these types of functions are continuous, just A, from your basic knowledge about quadratics and linear functions, but also B, because when you're doing this, you're just adding together a bunch of continuous things. If you add together continuous functions, you will still get a continuous function. Okay? All right. The next thing that we're going to talk about is the leading coefficient. Okay, what is the leading coefficient? The leading coefficient is just an. Okay, that might be confusing because what is an? Okay, obviously it's this thing up here, but what really does that mean? Okay, so maybe it will help if I gave you a couple of examples. Okay, 3 examples. We'll do one easy one that you've already seen before, 3x squared plus 2x minus 1, or 1. Alright, so here the leading coefficient, is just the coefficient in front of the highest power. So here the highest power is x squared. The leading coefficient is 3. In an attempt to confuse you, I will perhaps change it from a nice number like 3 to something ugly like pi over 2. Pi over 2x plus 2. Okay? Now here, this is a polynomial, right? It's still a polynomial. The only thing that's different now is that there's only one term, right? X here is the highest power that we have in our entire polynomial, and the coefficient in front of it is pi over 2. So this is our leading coefficient. Okay? And final example, in a further attempt to confuse you, I'm going to write it in a scrambled order. Okay? What is the leading coefficient here? Think about it. Yeah, it's not 1. It's not 1, okay? You have to look at the highest power, 3x to the 4, and look at the coefficient in front of it. In this case, 3. So the leading coefficient is 3. Why did I mention the leading coefficient? Why are we interested so much in this one specific number? That will have to wait for next lecture. Okay? But it's an important property, and I'm going to be using the terminology from now on, so you better write this down and make sure you understand it, okay? Let's see. Okay, so before we do this, I want to make some notes about how these polynomials look like, okay? What I want you to do is a bit of graphing first. And I want you to graph the following functions. I want you to graph just a general line like 3x plus 1, okay? So I want you to graph 3x plus 1. I also want you to graph, let's see, x squared minus 2x. Let's do x squared minus 1. Okay, yeah, let's do that one. X squared minus 1. Okay. Now I want you to look at how many zeros or roots these functions have. Okay, so just to remind you, a 0, or in other terms, a root of a function, is just a value x such that, st means such that, f of x is equal to 0, right? So for example, if my function did that, right, this is a root, and that is a root, okay? I can also call those zeros, okay, because that's when they hit 0. It's a pretty intuitive naming, right? So just list out for me what are the zeros of this function and what are the zeros of that function. Okay, you can do this. You can do this for now, looking at the graph. But of course, you've had a lot of practice, and you should be able to confidently do this exercise. I want you to find the zeros of this function and this function, right? So this one should be pretty clear. Remember, a 0 is just when y is equal to 0. So in this case, the 0 is negative 1 over 3. And here you should have two zeros, negative 1 and plus 1. Okay? Those are zeros of the function. Now, what you notice is that given any line, you can only have at most one 0, right? Here I gave you a quadratic, and it has two zeros. And if you just think about the general shape of quadratics and how they can sort of intersect the x-axis, it should be pretty obvious that there's only 3 options, right? And you've gone through this. You've gone through this in grade 11. There are 3 options for a quadratic. Either it never touches the x-axis, either it touches the x-axis just once, or it crosses the x-axis twice. And this corresponds to the 3 different cases, right? So in this case, our quadratic has no solutions, no real solutions. Here we have one solution, and here we have 2 solutions. Okay? So all this should be review, but I'm just going to reiterate it as a observation now. Similarly, for a line, we can only have really 1 0, right? There's no way to like really change it so that you have, for example, 2 zeros, right? It's just not possible, right? So let's note this down. So for the line, we have at most 1 0. For the quadratic, which I'll just write quad, we have at most 2 zeros. Okay? Now is a good time to bring up another term. So definition, degree. Okay? The degree of a polynomial an x to the n, an minus 1, x to the n minus 1, so on. I'm getting tired of writing this. It's just n. Okay? So in other words, it is the power on the highest degree term. A bit of thinking should convince you that a linear function is degree 1 and a quadratic function is degree 2. Okay? This is because quadratic functions always have an x squared term, and that's the highest power that they have. X squared is x to the power of 2, and so in this case, it is the power on the highest degree term. Right? The power on the highest degree term is 2 for a quadratic function. For a linear function, it's 1. Similarly, you may have heard of something called a cubic, right? A cubic. And a cubic is of degree 3. It's a degree 3 polynomial. That's what we call it. Now you notice how I've been writing this in purple and this in red. You may be wondering, is it true that a cubic has at most 3 zeros? And you'd be right. Yes. So this has at most 3 zeros. And now, I hope you catch on to the pattern. You know, these numbers are the same, these numbers are the same, these numbers are the same. Okay, so our conclusion must be that a degree n polynomial has at most n roots, or n zeros. Okay, I'm going to box this up because this is a fundamental, really, really important fact that we are going to carry through with us throughout the entire semester. Okay, this should be so ingrained into your head that you don't even have to write it down anymore at the end of the term. Now you should write it down, but you should be comfortable with this idea. Okay, you should be comfortable with the idea that a degree n polynomial has at most n roots and zeros. And of course, your experience has told you that for these two cases, it's true. If you graph some cubic functions, you'll be convinced that that's true as well. And if you graph more higher power polynomials, higher degree polynomials, you'll also see the trend that they have at most, n roots. Okay, so that's the notion of degree, and this is an important fact about degree and polynomials. Okay? Okay, so we're making really good progress here. Now, we are going to consider one more thing. Okay? So, just very intuitively, if you've played around with some polynomials before, you would know this, but in case you don't, a polynomial in general, so here's a fact, and I'm going to put it in quotation marks because this is not really a precise way of saying it, but it is a way of saying it when you're first starting off. A polynomial just looks like a squiggly line. Now, obviously, there's not much squiggle to that, and I'd be hard-pressed to call that a squiggly line. But as you go up the degrees, the polynomials become more and more squiggly. Right? So here what I'm doing is I'm drawing higher degree polynomials. So here's a degree 1 polynomial, a degree 2 polynomial, a degree 3 polynomial, a degree 4 polynomial, a degree 5 polynomial. Okay? Notice how as I increase the number here, the squiggliness goes up. Here we have like one bend, here we have a bend, and here we have 1, 2, 3 bends, and here we have 1, 2, 3, 4. Aha! I think I see a pattern here. If we were to measure squiggliness by how many squiggles the line does, maybe we'd be onto something. Okay, so first let's be precise what I mean by a squiggle. So a squiggle is like one of these things. Okay, but it's also like one of these things or these things. So how do I formulate that mathematically? Try and think about it. It involves a concept that we have actually studied so far through this course in the first unit. Okay, and the concept is increasing and decreasing. So a squiggle point, we're going to call it a turning point. That's the terminology that people seem to prefer. I don't know, I always say squiggle. But a turning point is a point where the function switches from increasing to decreasing, or vice versa. So here, this is a turning point because the function stops decreasing and starts increasing. Here the function stops increasing and starts decreasing, and then it does another switch again. It goes from decreasing to increasing. So here's a turning point, here's a turning point, here's some more turning points, here's some more turning points. Maybe you notice a pattern. Here there were no turning points. I'll write TP. Okay? And this is the pattern. Hopefully you see it. The amount of turning points is always one less than the degree. Right? So this was degree, remember? And here is just the general shape. Okay? Because a polynomial just looks like a squiggly line. That's the fact. Okay? So here is the real fact. Here's the real fact that I'm not going to put in quotation marks. Let me just make sure that this appears on camera. Yeah, we have space. Okay, so fact, a degree n polynomial has, at most, n minus 1 turning points. Okay? This is another fact that we're going to use a lot, but it's not until calculus that we are going to see for real why this is true. There's actually a very, very good reason why this is true, but it requires calculus to see it. Okay? So another thing to look forward to as we move through advanced functions. Basically, all of advanced functions should just be hyping you up for calculus. Alright, so here, no turning points, 1 turning point, 2 turning points, 3 turning points, 4 turning points. So the degree of the polynomial should always be 1 more than the number of turning points. Okay? Again, these two examples, you've had more than enough experience with them. As we go through these, you're going to get more experience with these degree 3, degree 4, degree 5 polynomials, and you'll eventually see that this fact is true. But for now, we can't do any more progress until I tell you this is true. Okay? Okay, so now we're going to go through some more stuff related to turning points. And in order to do this, I want to introduce a couple of concepts. So in a function, you may have noticed that you get often things like this, or things like that, and you know, these kinds of things, right? And it may seem pretty intuitive that these things behave in a way that is pretty easy to understand. Like, for example, this is the highest point if you look around any neighborhood of this little point here. Here's another high point, and here's another low point. Here's a high point, right? So we have terms for this, and it's pretty self-explanatory. It's maxima and minima. So maxima and minima. Okay? And in these cases, we have two different types of maxima and minima. They're called local and absolute. I'm just going to write abs. Okay? So perhaps it's easier if I illustrate these concepts just using diagrams. Okay? But then I'm going to put real definitions in here. So what I mean by a maxima is, of course, a point that is bigger than everything else around it. Right? So this is a maximum. what I mean by a minimum is just the exact opposite. It's just a minimum point, so a point that's lower than any point around it. Okay, so it should be pretty intuitive. The problem is what is local and what is absolute. So to do that, let's consider two graphs, right? So here's one, here's another, and the ones that I've drawn, I've tried to draw them so that they're polynomials. Okay, they respect the shape of polynomials. Okay. So here, we look at these two graphs and we can immediately identify maxima in each of them. Here's one, here's one. Okay? Notice that there's no maxima as we go to infinity because they're like, whatever point you pick, right, there's always a point if you keep going to the right that's bigger than it, right? So there's no more maxima. Here, this is the only maxima because these, this just keeps going down. Alright, so what's the difference then between this one and this one? The difference is, here, this point is the biggest around its neighborhood. So like if you look around it, it's bigger than everything else around it. But that doesn't mean that it's the biggest, it's the highest point on the entire function. In fact, I can just look here, and look, this point is higher than that one. Although you wouldn't be wrong in saying that this is a maximum point, this is just a local maximum point. Locally, it is a maximum. Compared to this one, which is bigger than literally anything else on the graph. Nothing will ever top this point. Therefore, it is an absolute max. Okay? And so that's the difference, right? Absolute just means over the entire graph or function, right? And this is over the whole function. And local just means locally. So like in a small neighborhood. Okay? So locally. Right? And maxima just means highest point. Highest point. And this is the lowest point. Lowest point. So hopefully those two concepts are pretty easy to understand. Alright. So what does this have to do with turning points? Remember what a turning point looked like? It was a point where the function switched from going down to up or up to down, right? And so what you naturally have is the creation of either absolute or local maxima or absolute or local minima, right? So for example, suppose we have ourselves a cubic, okay, and a cubic, you'll learn, typically has this form. It has two bends, right? Because there's two turning points, right? Let's see. All right, so let's classify the maxima and minima. So here we have a local max. So I'll write LOC for local and then MAX for max. This is a local min. There are no absolute maxima or minima because here this just goes down to negative infinity and this just goes up to positive infinity. Okay? The situation becomes a little more ambiguous when you have, for example, a quartic function. So a quartic function might look like this. Okay? So this is an example of a quartic function. Let's again classify the local maxima and minima. So here is a local max, right? And that's all the maxima I see, right? Here's a local min. And why is it a local min? Because it's not the absolute min. In fact, the absolute min is here. And why is it the absolute min? It's because no other point on this function is lower than that one. Okay? There is no absolute max, and this is not the absolute max because I can find other points which are bigger than it. Okay? So I hope that's pretty intuitive. Let's just go through one more example. And we're going to do a, how do you call it? It's a degree 6 polynomial. We'll just keep it like that. Degree 6. Okay? So remember, degree 6 polynomial has n minus 1 turning points. So n is equal to 6. So we should have at most 5 turning points, right? So we should draw something with 5 turning points. Let's do 1, 2, 3, 4, 5. Okay, so let's classify these. So let's just start off by circling all the points that we might need to consider. So it's all the turning points. There's 5 of them. Okay, now let's check which ones are the absolute max and min. Okay, this is the general approach. Okay, this is probably the best approach to solving these types of questions. So there's no absolute min, I can tell you that for sure, because this goes down to negative infinity. If there was an absolute min here, you could always pick a point that is lower than it. Okay, so there's definitely no absolute min. There is an absolute max though, it's right here. So we'll call this absolute max. And of course, here are 2 other maxima, but because they are not the absolute max, then they have to be the local max. Okay? And just to be picky, if 2 points are the highest among the entire graph and they are both at the same height, then both of them are the absolute maximum. The only reason why I knew instantly that these 2 were local maxima were because they were both lower than this one. So they definitely could not be absolute max, but they were definitely local maxima. Okay. In the same way, these 2, because I know there is no absolute minimum, these 2 must be local minimum. Okay? There we go. So that's all. So that's the connection between a turning point and this concept of maxima and minima. Again, as with all things, this is going to come up even more in calculus, so it's important that you at least understand this idea, right? This idea of maxima, minima, local maxima, absolute min, absolute max, okay? Alright, so we're almost getting there. Again, like, this lecture is really a mess. There's a lot of ideas that I need to go through before we start doing any real work. But hopefully this is a nice change of pace. It's a lot of intuition, lots of pictures to be drawn. Right, okay, so now we have to tackle end behavior. Okay. So the best way I can think about end behavior is splitting it into 2 cases. Okay, so we have even degree. So remember, degree is just the highest power in your polynomial. Even degree and odd degree. Okay? So just think about raising a number to a even or odd power. Okay? Think about like x squared, for example, or x to the 4, or x to the 6, and so on. Here we're going to think about x cubed, x to the 5, and so on. Okay. What happens when I start putting really big numbers in here? Well, they start getting really big, right? So as x approaches infinity, so that means as x gets really, really big, right, x squared also gets really, really big. And as I put negative numbers in here, well, the square is an even power, right? So it actually multiplies it twice, and so negative numbers will become positive, right? So as x gets more and more negative, as x approaches negative infinity, it happens that x squared also approaches infinity, not negative infinity. So in general, the graphs of these even degree polynomials will end up going to infinity at the very ends. Okay? Some interesting stuff might happen inside this box, but we don't care about that right now. We just care about what happens at the very end, right? And this is called end behavior. Using limit notation, we can write this really nicely. We'll write it like this. So limit as x approaches infinity, or limit as x approaches negative infinity, and we just found out that for even degree polynomials, f of x, right, this is equal to infinity. Now, again, remember, infinity is not a number, this is just notation to tell us that as x becomes really big, so does the function. And as x becomes really negative, the function becomes really big. Okay? Now, what happens if you do odd degree? The situation reverses itself, right? So as x approaches infinity, x cubed, or let's just do x, right? X, well, I don't even have to write anything, right? But let's just do x cubed. So x cubed approaches infinity, But as x approaches negative infinity, right, that's a negative number to an odd power. So that will also approach negative infinity. So that means that in general, our odd degree polynomials will go to negative infinity as x becomes really negative, and will go to positive infinity as x becomes really positive. It might do some interesting stuff in the middle, but we don't care about that right now. We just care about the end. So, to write this in limit notation, we would write limit as x approaches infinity of f of x is equal to infinity, and limit as x approaches negative infinity of f of x is equal to negative infinity. Okay? So hopefully that's pretty clear. Now you may be wondering, why am I doing all this? And the goal is to basically be able to graph any polynomial that I give you. That might seem like a very daunting task, but we're actually going to get through it in the next couple of lectures. Okay? All of this is preparation for doing that. So for example, let's just take a break from new terms and stuff and just see the application of what we have so far. Because let's say someone wanted you to graph the function, let's do x plus 1, x minus 2 times x plus 4. Okay? Now you might look at this and say, hey, that's not a polynomial, right? It's definitely not. It's not in the form. And you're right, it's not in the form. However, that doesn't mean we can't multiply things together, right? If f of x is this thing, we could multiply it out together, and it would end up being a polynomial. You can try this out yourself. You'll end up getting a polynomial. But I actually want to look at this factored form right now, because there's a lot of interesting things that we can say once a polynomial is in factored form. Okay? And this is the next idea that we're going to explore. But I want to piggyback off of this, using first the ideas that we've developed so far in this lecture, which is about to end in, I'm estimating, another 5-6 minutes. Okay, so we want to graph this thing. Okay. Now we're going to have to put everything that we learned today about polynomials to use if we want to have any chance at doing this. So the first thing is we need to figure out the degree. You can go and multiply this out yourself. You'll find that this is a degree 3 polynomial. Our two facts regarding degree and polynomials tell us the following. Firstly, it can cross the x-axis at most 3 times. Our second fact tells us that there will be at most 2 turning points. Okay? Now, what did we just look at? We looked at end behavior. So we can write some things about the limits, right? So all I'm going to notice is that this is a degree 3 polynomial, and the first term is going to be something like x cubed, right? So this is equal to x cubed plus some other stuff. Again, I want you to expand this out and figure out what it is, but this is really the only thing that is really important right now. Okay, this and one other thing, but I'll touch on that later. Okay, so yeah, because this is an x cubed right here, we can use the fact that we just learned, which is that limit as x approaches infinity of f of x, infinity, and the limit as x approaches negative infinity is equal to negative infinity. So we know that at the far ends, this function has to do something like that. It has to go to negative infinity as x becomes really negative, and it has to go to positive infinity as x gets really positive. Okay? Now, what else can we figure out? We need to figure out how this thing looks like in the middle. And so far, all we have is this. It's not much information, but that's where I'm going to use this here. So what I'm going to do, and this is actually the most useful thing. Let me just write down here the moral. The moral of this example is that knowing the roots is 90% of what you need to graph the polynomial. Okay? Now, this might sound like a ridiculous statement. How can just knowing the zeros of this polynomial tell you so much? Well, it all has to do with what is going on here, the end behavior, and what we know from this. Okay? And let me illustrate that. So firstly, what are the roots of this polynomial? Remember, a root is when the function is equal to 0. So we need to set this thing equal to 0. So let's do that. Now, because we factored it, these are really three different numbers. X plus 1, x minus 2, x plus 4. Those are three different numbers. And if they multiply to give you 0, well then, one of them has to be 0. Right? At least one of them. So we're going to go case by case. What happens if this one's 0? If this one is 0, if x plus 1 equals 0, you can solve this in your head, x is equal to negative 1. So we know that there is a 0 at x equals negative 1. This is the exact same procedure that you did with quadratics. It's the exact same one that you use when you graph quadratics. So in a similar way, I can figure out the other zeros. They are 2. Wow, negative 1 is very far today. So let me just change it up like that. And that should be correct. Okay, so now, does this agree with what we have here? Well, yeah, it crosses the axis at most 3 times. In fact, right here, we do have it exactly 3 times. Excellent. Okay, so now let's fill in the rest, knowing that there is at most 2 turning points. Okay, so 2 turning points. I don't know if you can see it, but I kind of see that this is sort of like the most natural thing for this cubic to do. Because we know there's at most 2 turning points. So, 1, 2, we're done, right? Now, obviously, I didn't draw it very accurately, right? If I was doing this for real, I wanted a little bit more information. I'd like to do a little bit more, and we're going to work towards doing that, getting all the details filled in as we move throughout this unit. But so far, this is what we get, and this is actually pretty much all we needed to do. There's only 1 or 2 little things more that we're going to have to do, and then we're going to be done graphing. Okay, so this is really neat because just this very vague knowledge and this simple idea of multiplying numbers together to give you 0 was enough to graph a pretty good sketch of the polynomial. Now I would like you to actually graph this thing. Go on Desmos, graph this thing, make sure that it lines up with what we have here, and maybe in a separate sketch you can figure out what maybe we didn't get so right. So for example, did we get the y-intercept right? I can tell you right now that the y-intercept is actually negative 8, right? It should be negative 8. So this doesn't really look like negative 8, so maybe that's one refinement that we can make to our drawing. The other refinement that we can make is with this, okay? Now, here's the problem. This one we're going to explore in the next lecture how to get this. It's not that difficult. This one is a lot more tricky. To get this point right here, we're going to need calculus. Okay? So one of the first things that we're going to be doing with calculus is drawing really, really accurate graphs about polynomial functions containing all the important information. And by important information, I mean the zeros, the x-intercepts, the y-intercepts, the end behavior, the local maxima, local minima, absolute maxima, and absolute minima. Okay? Right now, you're not expected to do this. Right now, you're just expected to be able to reason out that, oh, I just need to connect these 3 together in such a way that there is at most 2 turning points. Let me just show you a bad example of someone doing this question. So, sorry. Remember, our zeros were negative 4, negative 1, 2. Okay? I'm just going to be really rough here. A bad example would be someone trying to do this. Okay, here we have too many turning points. Okay, like this is just straight up wrong. There's no way the function could look like this. Another thing that would be wrong is if we got the end behavior wrong. Maybe you weren't paying attention to the limits and you forgot which way the function went, and you thought maybe it was like the quadratic case where they both start and end at infinity. So maybe yours looks like this. But you just created another root here. Like you can't do that. And maybe you wanted to be clever and say, oh, well, what if I just do that? Well, no, that's also wrong because, look, you had to have at most 2 turning points, and you have 1, 2, 3. Okay? So in the end, all of these are just logic puzzles. This was really helpful. This was really helpful. And solving this here for 0 was also very helpful, right? So again, moral, it's right here. Write this down. Very important. Okay? Knowing where the roots are is 90% of what you need in order to graph the polynomial. Okay? And hopefully this example has convinced you of that. Now, this is like the very simplest example that you might be given to solve. Over the course of the next couple of lectures, we're going to see how we can make these examples more sophisticated and actually go backwards. So remember how I asked you to multiply this out together to give me something in the form of a polynomial? I'm going to show you next lecture a method for going from the polynomial to a factored form. The factored form is really important because that's what got us to use this trick. That's what got us to use this, and we were able to find all the roots just by having a factored form. 90% of the time on the test, you're not going to get a polynomial in factored form like this. You're just going to be given a straight polynomial, and you have to factor it. So again, it sounds like a daunting task. It is quite difficult at first, but I assure you that we can get through it, and it will be very rewarding at the end to be able to graph these things. They actually turn out to be pretty fun puzzles at the end.